All right, so you should have this document, the Lemon Student document, whatever. It's got 3 tabs. Everybody get that? You can open it. You just open it up once you logged in. Just choose open, and you should get right to this screen here. Okay, so what you're going to do is when we're going to take some measurements on the lemon, and take some measurements on these lemons and put those into this kind of spreadsheet, and then we'll draw a graph and then so forth and so on. So, so each group will need a ruler, and all right, so on the front of this page, then you'll put in your width and your radius. Now, on the front of your document here, okay, if you go down here, so what's going to happen, you're going to take your lemon, so you're just going to pick out a lemon out of the group here, okay, it's going to tell you to slice off kind of these bulbous ends here, these little ends, so just kind of, so careful. The administrators don't know I do this. I don't know if they get in trouble for having a knife. Surely we got no food group, right? Okay, so just kind of slice those off so it's kind of flat on that end. And just like this, you're going to set your lemon down so it's right through the halfway, right? The x-axis is going halfway. Now these lemons aren't going to be perfectly symmetrical, so we're going to be off a little bit in our calculation, but it's going to, so that's you're going to draw like the top half of the lemon, okay? And then it's going to lead you through it. As you read the directions, what's going to happen is that we're going to divide this up into 6, and we'll measure it in centimeters probably. So your lemon, and then you're going to measure it, right? You're going to measure how far, and you're going to divide that into 6 equal subdivisions. You might have to round to the nearest tenth or whatever, okay? So we're going to divide that up into 6 equal parts, and then you're going to measure, so 1, 2, 3, 4, 5, 6, and then you measure the height of that, right, at each of those marks. Now, that'll actually be, what will that be on the lemon? What would that be on the lemon if we measure from the middle out to the edge? It'd be the radius, right? It'd be the radius. Now, you would expect that the radius is a little taller in the middle, right, than it is over here. And then you're going to slice it, right? And so then you're going to mark on your lemon, right, with your pencil or whatever, 6, at those 6 places, and then we're going to try to slice the lemon into 6 equal slices. That's where it gets pretty tricky, to make it perfectly equal width and really good slices. But you'll pick somebody in your group that you think will be good at slicing it, okay? We're going to calculate the volume of the lemons in 3 different ways. One way we're going to calculate the volume of the lemon is by dunking it in the water and doing displacement, okay? I'll tell you how to do that, or need you to do that. Then so obviously you do that before you slice the lemon, right? So follow that direction, okay? So you'll do that. Then to make your measurements and all that stuff, divide it up into 6, you make these measurements, and then down here at the bottom, so right here you'll put your 6. Now they already put 0 in here, assuming that your lemon would hit 0 here and here, but it might not because of those ends. So your lemon might actually kind of hit the y-axis up here a little bit. So if you have a y value here, just cross out that 0 and put an actual y value in there, it's fine. Okay, I think on the one I did here, I did have 0. Here's an example one I did, and then we draw the graph of it. Okay, well, I'll show you that here in a minute. So you put your data from your table, here, this table, into your calculator, okay? Then you're going to get an equation to fit that. I'll show you that here in a second. Okay, here's where you're doing the displacement volume. Here's where you're going to do your slices. Okay, you're going to calculate the volume of each slice, because each slice is basically going to be what shape? What shape will be the slice?
Circle.
Well, but it's 3-dimensional. Circle's not three-dimensional. It basically be a cylinder, right? Now, it's probably not going to be perfectly straight up and down. It'll be slanted. It might be more like a, what would you call that? Peanut butter cup? It might be more of that kind of shape. But we'll call it a cylinder. If you want to, you could do an average. You could do a radius on this side, radius on this side, do an average radius, right? You could do kind of an average radius, and then do your cylinder, right? And so you're going to do the volume of each of your slices and add those up. So we'll have our displacement volume. We'll have our calculation of adding up the volume of the 6 slices, okay? Especially when you get to a slice on an edge. You know, your slice on one of the edges, your very last slice might be, you know, more like that, you know, kind of a thing. So your slice on the very edge. So you really have to do an average radius on that thing. And then we're going to do the calculus part of it, okay? Now, where the calculus part of it comes in, is we use this, so on our calculator, when we go to this page right here, we got our width and our radius. So these points will show up. You just click down here, and we want our width to be our x, and you click over here on the y, and we want our radius to be our y, and there's your little picture of your points, right? So that'll be a little picture on your calculator. And then we simply go over here to menu and analyze and regression, and we're going to do a quartic, which is a 4th degree equation, and boom, it's going to fit an equation to that, and we're going to use that equation. Now, if you really want to see it, you have to drag it, which is kind of hard on your calculator. So if you go to page 3, it's got this page for you, and it's got this already in there. You just hit enter, and then we call that R of x for radius. Instead of f of x, I called it R of x. And then if you just type R parentheses x and hit enter, there's that equation, and then you can just arrow over it, because you're going to have to write that down on your paper, this equation. Okay, you're going to use that. All right, so let's go to it. So each group needs a ruler, a lemon, take one of the things of water, a few paper towels, go. Girls in one group, guys in another group. If you get stuck in somewhere along the way, let me know, and I'll prod you along here so we kind of keep going. Let's see what we've learned from this. Now, so as you notice, at some point, if you read along in there, it talked about how we're finding the volume of this lemon by revolving a region. So let's go back to here. And so if we go back to the front of this, what we did is we drew, you know, this top half of our lemon, right? So it's like saying, okay, here's this region, right? So think about what we've been talking about. We actually gave this a function name. We called it R of x, but it could be f of x. But this, we actually said this could represent some function, right? Some equation. And we are going to revolve this. Now you have to think of it like this. Yeah, oh shoot, I can't. You know though, every year I said I should buy one of these, and I never do. You know, like those party decorations that come folded up, and then you unfold them, and they make a 3-dimensional shape? That's what we're talking about. You know, so, you know, I always think of the old, like the bell, you know, so it's this flat kind of thing. It kind of goes like this, and then it kind of does, I don't know, something like that. And then when you unfold it, it looks like a boot, but when you unfold it, it looks like a bell shaped kind of a thing. That's an awful bell, but you know what I mean? So I was thinking of a bell. What other kind of sphere, right? You could have a half circle, right? I mean, that's kind of what this looked like a little bit, but it's kind of oval. But that's what I always think about. Revolving, so you take a flat 2-dimensional region and you revolve that around an axis, and it creates a three-dimensional solid. So what we have to do is we imagine, so that's why I did the top half of the lemon. Now this lemon's not symmetrical, right? But we take the top half of this, we revolve it around the x-axis into the other room, if there was another room. Mrs. Larson's room. Oh, it's not Mrs. Larson's room anymore. It used to be in the old school. She was next door. But whatever, there's no room over there. But if we take this region, revolve it around it, come up off the page, go into the other room, it would create the lemon, right? That's what we're talking about. So whenever we have one of these problems, it says, here's a region, find the volume of the solid. When you revolve that region around a certain axis, that's what we're talking about, right? We're creating a solid. Now, how do we use calculus to find the volume of that solid? Well, as you saw at the end, we're adding up stuff, right? What did you add up? The slice volumes. So what we need to do is find the volume of one slice, right? And then we can use the integral to add up all the slices. Now, you guys did 6 slices. Now, they weren't very accurate, were they? Well, because of our slicing, our cutting. But even then, they weren't really cylinders, were they? They were peanut butter cups, right? Really. But if you did 10 slices or 100 slices, right, then they would start getting thinner and thinner, and then you wouldn't have to average the radius, right? It would pretty much be, right, a cylinder. It would be getting closer and closer. So if you did an infinite number, it would be like adding up the volume of an infinite number of slices. Now, they'd be paper thin, just like a piece of paper is technically three-dimensional, right? I mean, we talk about a piece of paper being two-dimensional, but there is some thickness to this, right? Very, very little, almost negligible, but that becomes the delta x or the dx. Okay, so think about what we're going to do here. We're going to just put in one strip here. Remember the work we did with strips and top minus bottom, right? Kind of calculation. The height of that strip, that is going to be, so if this is my x-axis right here, we're going to think of it this way. We're going to think of a strip sitting on the x-axis, and then we're going to think about revolving that. And look what does that create? Creates a circle, right? So we're going to have a circular slice. Now, Tim said circle earlier, and I said, no, it's three-dimensional, right? But if we have an infinite number of them, it almost becomes two-dimensional, right? Because the thickness is going to go to nothing. That's going to be the delta x. So we're creating these slices, and this strip, we're going to have to think to ourselves, what does this strip represent? Now, we're going to do problems where we're going to add up a lot of different slices. Circular slices, but other shaped slices too. So we're going to have to identify what the slices are. But right now, for today, we're just going to stick with circular type slices, okay? Because we revolve this strip, and it's going to create a circle. And this strip is the radius of that circle. And so that's what we were trying to get across there at the end of the packet. For you to understand, this is r of x minus 0, right? Top y value minus bottom y value, right? Top y value minus bottom y value is the length of this strip. This strip represents the radius of one slice, right? The radius of one slice. So, when we get back to here then, this segment is adding up all of these different volumes, right? All 6 volumes. So when we get to here, what would the volume of 10 slices be? Well, it would be I equals 1 to 10. And Emily, this is where, and Skylar, this is where I was going to tell you we would fix yours a little bit. So, what are we adding up? We're adding up volume of a slice. What's the volume of a slice? Pi r squared h, right? So it's going to be pi. Now, what's the r? R of x. Now, the problem is we can't technically, so Emily and Skylar, you guys had this in yours, we can't really put r of x here because each one's going to be different. So when i's a 1, when i's a 2, when i's a 3, right? What was your guys' 6.6 was your total width? What was your total width? 6.5. So it's pretty close. So theirs was 6.6. So let's take, so if their total width was 6.6 divided by 10 widths, that'd be 0.66, right? So theirs is going to be 0.66 I is what's going to be in here. So for you guys, it'd be like 0.65 I if your total width was 6.5. So that means when I is a 1, we would do the R value at 0.66, and then at 0.66 times 2, 0.66 times 3, 0.66 times 4, right? These would be all the strips, right? Like when we did sigmas before. And we're not going to have to do this in our calculations, but that's how we did our sigmas, right? And then we had to times by H, right? What's H? That's the delta X, but in our problem right here, their problem, it would be 0.66. So we would times by 0.66. Remember in our sigmas, we'd have things like 1/10 there, or 3/10 or whatever our width was, right? As a matter of fact, a lot of times that got pulled out in front too, right? So that's what it would look like. So yours would be like 0.65, right? And what if we were doing 100 of them? Well, I would go from 1 to 100, and then be pi, and then it'd be R of, what, 0.066 squared times 0.066, right? I mean, that's what, right? I, yes, I need an I. Yes, need an I inside there. Okay? So that's what it would look like if we wanted to add up 100 slices. Well, what if you wanted to add up an infinite number? What would you put? Integral from 1 to, no, we don't put an infinity up here. We go 1 to n. We go 1 to n, and then what do we put out here? Limit at, right? That's a definition of an integral, right? The definition of an integral is a sigma from 1 to n, and then it would be n goes to infinity. And what would be in here? It would be pi, and then it would be r of, no, what did we do here? We did 6.6 divided by 10, then we did 6.6 divided by 100. So this would be 6.6 divided by n times I. And this would still be 0.66, right? Oh, no, it wouldn't be. That wouldn't be 0.66. It's our width. It'd be 6.6 divided by n, right? It'd be 6.6 divided by n. Here it was 6.6 divided by 10, 6.6 divided by 100. Here it's 6.6 divided by n. So that's what our sigma would look like here. What is the general calculus name given to this infinite summing process? The definite integral. Definite integral. Write a specific calculus expression for the volume of the solid. So this right here should be the volume of your lemon, right? It's an adding up an infinite number of volumes. Notice, and the key is we're adding up volumes. Pi r squared h, pi r squared h, pi r squared h. We're adding up infinite number of volumes to give us the total volume of the thing. So it's going to be the integral from yours would be 6.5, right? Times, and then it'd be pi r of x, or we could call it f of x, but I'm going to call it r of x. Are you sure there's not a 0.66 or something in there? No. Integral, or sigma, messy, integral, not messy, right? Neat, clean, whatever. And then, what about this delta x? That becomes the dx, because when we have an infinite number of slices, the width just kind of disappears. And remember when we were doing the arc length problem, we said we have to come up with an integral where we have something that's disappearing and becomes the dx. Well, in our slices, it's that width becomes that. So, remember when we were doing this, and we had a quiz where I asked you, I said to explain why this is the area under a curve. What did you tell me? Why is this the area under the curve? Because the integral is adding up, well, it was actually the sigma. It was adding up an infinite number of rectangle areas. Why were these rectangle areas? Because this is the height of the rectangle, and this is the width of the rectangle. Well, why is this the volume then of the lemon? It's pi because the slice, because we're adding up infinite number of, what are the slices? What shape are they? Cylinder slice volumes, right? We're adding up an infinite number of cylinder-shaped slices. And this is the volume of a cylinder. Pi times radius squared times height, right? Pi times radius squared times height. And so this is adding up, and this is adding up volumes. So that's why it's going to be a volume. And think about it, the radius is centimeters. You do radius squared, that's centimeters squared. What's the width? Centimeters. Centimeters squared times centimeters. Centimeters cubed. We're going to get volume. We're going to get volume so it all fits. Okay? All right. Now, so for our general kind of thing that we're going to talk more about tomorrow, we got the dx part. What is that then? What is pi r squared? That's area, right? Now, when you first in middle school learn about volumes of prisms and stuff, it's area of the base, it's area times height. That's what it is. It's centimeters squared times centimeters. It's the area, so you got the circular area, and then you got the height, right? So what our general, and we'll write this down tomorrow, what our general formula for volume is going to end up being this right here. It's going to be that right there. Because area, centimeters squared, times height, centimeters squared times centimeters gives you centimeters cubed, right? So what we're really going to be looking for is we're going to identify our slices. We're going to think about the volume. We're going to think what shape are the slices. For the lemon, if you think about slicing the lemon, the shapes are cylinders or circles, like Tim said. We can literally think of them as two-dimensional now. We can think of them as circles because the dx is the width. They're paper thin. So we can think of our slices as circles, and so what we're going to want to put in here is pi r squared, right? The area of a circle is pi r squared. Well, but the key is the r is going to be a strip. The r is going to be a function. It's going to be a strip height. That's going to be our radius. So we're going to think of it this way. We're going to think here's our axis. Here's our strip, right? And it's revolving and it's creating radius. Okay, that's how we're going to do this. So, let's do a problem from our sample 3 packet.
The last step in the packet is write a letter to an absent class.
Oh, yeah.
Say what you learned.
Max.
There you go. We could send it. So, Max should send a letter to Will. We should all draft a letter to Will.
Max has got it covered.
Max has got, yeah, I want to say like double space. Yeah.
It's just like explain in a double space. Using
I know.
proper vocabulary.
I use it. Yeah, now, what would explain how far off our function was? Our function calculator. Yours was way far off, but yours was even pretty far off.
Initial measurements.
You had to draw with your pencil, around that lemon, and so that wasn't very accurate. And then your measurements, and then the regression equation isn't a perfect fit to that, right? Displacement's probably the most accurate, right? Even though we don't have a lot of markings on there, that's pretty accurate. The other thing is that lemon's not symmetrical, right? So when you were measuring your slices, you were taking that into account because you were doing a radius, and a radius and kind of averaging it. So those two, it makes sense, are pretty close. But since it's not that symmetrical, the lemon's not perfectly symmetrical, and those measurements we had and put into that function and then do it, that error became magnified. So it's pretty typical that our integral we do is not a great match because of the hand-drawn picture and the measurements and so forth. So it's not too disturbing that was off. Okay, so let's go to number 30 here in your packet. On sample 3. Okay? I don't know what page is that on there? Just 85. So sample 3, page 85. All right? And so this is the kind of problem we've been seeing and we've been skipping, right? So the region in the first quadrant is enclosed by the x-axis, okay, It's in the first quadrant. Closed by the x-axis, the line x equals pi, so over here is the line x equals pi somewhere, okay? And the curve y equals cosine of x. So, go on your calculators and graph cosine, just go on your sketch pad and graph cosine of x. And this would be a perfect one to do a zoom fit kind of thing, okay?
Does it matter that it's rotated about the x-axis?
We're going to get to that in a minute. Well, that's what we did the lemon. We had that region, we had that half a lemon, and we rotated it around the x-axis, and that created the lemon. Right, but let's get the graph drawn here first. So let's get the graph of cosine x. 0 to pi. So this would be an important one to do on your calculator. It would be an important one to draw a graph. Zoom fit would work really good. I think when you get it, it kind of looks like that. It's kind of this region right here. Well, but if you do a zoom fit, I think if you do a zoom fit, if you said 0 to pi as your win, and at the end of the day, it doesn't matter. It's as long as you know. Oh, you did it in the relation. So zoom fit maybe doesn't work quite as well in the relation. One, maybe. I don't know. It doesn't matter though. It doesn't matter if you drew yours a little flatter or whatever. But here's the thing. Here's what this picture would look like then. So now, everybody look up here. So this would be like our top half of our lemon right here. We are now going to revolve this region around the x-axis. So the other half, now you don't have to draw this. I'm going to draw it, and sometimes I will draw it, sometimes I won't. But the other half of this would be down here like so, right? Now, let me try, I'm usually not very good at this, but let me try to draw in one slice. Now, I'm going to draw my strip. Everybody, I think, should draw this strip right here, right? We want to draw a strip. But if we revolve this around the x-axis, ooh, that's not bad. Do you see how that would create a circular slice there? You see what I'm talking about? Now, you don't have to make this drawing, but do you see what's happening? You see as we take this and we revolve this around, okay, we get this. Now, what is my strip? What part of that slice is my strip? It's the radius, right? It's clearly the radius of that circle. It's the radius of that circle. So I'm going to set up an integral, and I know the volume formula is pi. Now, I usually like to write it off to the side. So what is my strip? I like to write it off to the side. You'll see why tomorrow. What is my radius? It is the top y value, which is cosine x, minus my bottom y value, which is 0. So, I'm going to have pi times cosine x squared, and then pi r squared h, right? My dx becomes right there. Pi r squared, and then my dx. And it's going to go from what to what? My strips are going to fill the space. See how it's the same lingo we were saying before? My strips are going to fill the space from 0 to pi. Okay, type that into your calculator on your calculator page. Just type that in right there. Make sure you get enough parentheses around that cosine business. Did you get an answer that's there? All right. What'd you get? C? You got C? Okay, now, here's the last thing I'll leave you with. Okay, last thing I'll leave you with. So we're talking about doing this right here. Okay, we're talking about having some region. We're talking about revolving it around an axis. And we're talking about creating a three-dimensional. Everybody look up here. Watch this. This is what we're talking about. Now, it's nice to be able to picture this, but you don't have to work the problems. But what we're talking about is that. Right? What we're talking about is that. Just like our lemon. We took that region we drew on that first page. We revolve it around. That creates the lemon. So you see the solid? Look at your strip right here. This strip is clearly the radius of that. That's what I was trying to draw up there. I was trying to draw like one revolution, right? And so to find the radius of this, we're saying the integral is going to add up all those slices. And notice they call that f of x. Well, isn't that strip the radius of that slice, right? And here it again, the idea of adding all that up to get the volume. And then in this case, our integral, well, but, okay, so again, the idea is, oops, no, revolve. Totally messed it up. Okay, but now what we're going to get into tomorrow, is what if you revolve it around here? Now what kind of slice do you have? What do you call that? Oh, what is this? What is this? That's your slice. What shape is that? What shape is this? Well, it's got a hole in it. What do you call that? Donut?
Is that really what it's called?
Well, washer. It wouldn't be like a washer. You know, a washer in with a circle with a hole in the middle, right? You call it a donut, right? We know all different kinds of shapes of slices. So or ring. Some people call it a ring. Okay. All right. So we're going to get into some pictures, some things like that. But again, the key is we look at this strip and we imagine as this revolves that's going to be the radius of a circular slice, and our integral is going to add up all the slices. That's what we're doing. All right.